So the question is there a way to get an allocation that matches what you need? In other words, get the hardware that matches what you're what you would prefer to use for the communication pattern. So that's sort of outside of the scope of MPI. Doesn't mean it's not a good question, but it's outside the scope of MPI. The resource managers that mediate the access to these machines can provide some of that capability. So it depends a lot on those systems. I think, Roy can correct me if I'm wrong, I think you can make some requests about the specific shape for the blue jeans for some versions of the crays. So for example, in blue water is you can ask for certain shapes, in fact, certain specific nodes. The consequence of that, though, is that it may be a long time until the shape is available. So it's better to, if possible, to design the code so that it can adapt to whatever shape it gets. Things could be even worse, which you see up here, is that on systems that allocate the nodes as they find them may give you something that looks like this. So it's not a brick. It's a collection of nodes with various pieces or occasional holes. So this is from the Blue Water system in Illinois, which is actually the largest system Cray's ever delivered. It's a very large system, but for example, there are holes in the network where there are I/O nodes, which has the positive effect of providing better access to the I/O system from the jobs, has a negative effect that there are these holes. And the system may give you nodes out here and so forth. The current system that's running strives to make things more compact because, in fact, despite years of the vendors, and it's not just Cray, claiming that topology doesn't matter, when you do the data, you find out it does matter, which is why asking for specific shape sometimes makes sense. And so it's become important at least to be aware of the issue. There is some cost to having the physical topology of the network not match the logical topology of your communication. Another thing which was going to make this more challenging is the next generation of systems do not have meshes. They all have high radix, low diameter networks which have obscure properties, maybe the best way to say it. Again, there's a tendency to say the network is perfect, don't worry about it. The realities have already shown that it just means that the problems are in different places. And so again, arranging your code so that it's more tolerant to these issues may in fact be the best solution. So one of the things I'll show here, and then I come back to a little later, is that if you organize the code, so we'll look at a halo exchange around sort of a communication phase, that may in fact be too rigid and too dependent upon things outside of your control in terms of the topology mapping. So as we look at the influence of topology, we find all sorts of things to worry about. We've already talked about the performance irregularities. So the fact that you have divided your work up so that the work is the same doesn't necessarily mean that the time to perform the work is the same. It certainly doesn't mean that the time to communicate between the elements is the same. So even if you do a perfect job of decomposing your work, you don't know that you have load balanced in the sense of making sure that each piece takes the same amount of time. And this can lead to fairly persistent load imbalances, which will be fine because they'll usually be relatively small for a few hundred, maybe even a few thousand nodes. But as you get to extreme scale systems, these can become quite crippling in terms of scalability. And so, again, the impact can be quite large. So for example, let's go back and look at the sort of halo exchange. So here's the way I'm going to think about it. But now say that this is really the logical way of doing it. Okay, so that's the way I think about the code. I have this process talking to these processes. But say that it doesn't get mapped. The physical processors that are representing the nodes, aren't actually mapped the way I think that they are. So I think that this process is next to this process, so I sent to it. But in fact, the way it got laid out on the system, they weren't adjacent. And then say that the way I wrote the code, this process is talking to this process, thinking that they're neighbors, and they are the way I look at it logically. But if the way it was laid out on the hardware is like this, you'd find is that this link here is being used by messages that in a sort of perfect layout would be going over separate links. Well, the consequence of that is that link has twice as much data moving along it as I'm thinking about as my execution model, which has a perfect mapping of the processes to processors, might have. And so that's an integer multiple in terms of the amount of data, so an integer divisor in terms of the performance. And so moving twice as much data, it's going to move half as fast. And so these can have a significant impact into the overall performance, and that can impact the effectiveness of your work balancing. I'm going to say work balancing as opposed to load balancing across the system. Okay, and then real patterns can be much worse, and particularly on systems where, for example, you end up with one process at a strange part of the network. So we've seen this on mesh-connected systems where the nodes are not allocated as a big solid. You might end up with a few nodes out here, and not only are messages going further distances, but they're crossing part of the system that's being used by other jobs. And so the data that's going along this link might not even be my data that I'm competing with. So it's important as much as possible to try to avoid depending on the communication performance being dedicated and lockstepped to your application. The more flexible you are, the more you defer synchronization, the less you're going to be impacted by an unfortunate layout in memory, unfortunate communication patterns. So for example, I remember many years ago running on a machine with a mesh, and you got a nice block, and we were doing benchmarks, and communication was terribly slow. And we eventually discovered that the file system was on this side of the machine, and the backup was on this side of the machine, and the data was running across the entire machine, including all of our nodes in the middle. So it wasn't even our job, but other data was moving along the system. You can have that now, even on these mesh-connected systems, and on the upcoming systems with these high-radix, low-diameter networks. A lot of your links are going to be shared by other jobs running on the system. And so you're going to be impacted by other things that are going on. We can look, and there's a number of different things going on in these tables. One of the things I've been asked by some people about whether the MPI topology routines ever help. And so I wanted to show that, in fact, there is an existence proof. There's some places where it does matter, but also places where it doesn't. Okay, so this is an example. The code is just sending 2,000 doubles, so 16 kilobytes to each neighbor. Numbers in the table are megabytes per second. And this is BGQ. So if I use ComWorld, well, first I did the example. This is the I receive and send example from the morning. So I do all I receives, then everybody does their sends, get an effective communication rate of about 660 megabytes per second. If I used a different layout, it was about the same at 711. If I did just I receives and I sends, so what I suggested you should do at the end of that discussion, the rate went up to, for MPI COM world, it went up to about 1.2 gigabytes per second. And if I picked a different topology, I got about 1.4 gigabytes per second. And interestingly enough, if I just set up a situation where I have one process sending to its 8 neighbors, those guys receiving and nothing else going on, so there's sort of the minimum amount of possible contention, that ran at about 2.9 gigabytes per second, or about double this, which is sort of what you'd expect, which is very nice. On the Cray, get these numbers, the I receive and send, and the I receive and I send, in fact, gave me about the same numbers. Changing the layout didn't help much, but interestingly enough, one sender gave me about 5.5 gigabytes per second, which is a lot more than this. Now, at one point I thought that this was a topology effect, but in fact it's something different, and I'll talk about that a little later after we've covered some MPI 3 things. And in fact, we can look at the historical performance of these. The blue genes have, the performance has improved as we've gone through L to P to Q in terms of the sustained rate. We've also seen some improvement in the Crays, and we can look at the ratios to a single sender versus having everybody participate. And interestingly enough, for the blue genes, the ratio has typically been about 2, which means that the communication is just happening the way you sort of expect, the way you model. Whereas with the Crays, we see a different effect, which is that the ratio is much higher. In other words, the performance when I have one process per core communicating is much lower than I would have expected based on having just one process communicating, and it's been getting worse with time. Again, this is actually not a topology effect. It's an SMP effect, and I will talk a little bit more about that. The key here for the blue genes is the way the network is organized is there's a separate network link driving each direction. And as I add processes, I'm just making use of each of those links. Whereas in the Cray, there's one connection to the network, right? And so as I add processes, I'm competing for the same resource. And so we can look at this again a little more in depth, and you'll see that it's a fairly fundamental feature, and it's going to be a very important feature in all of the upcoming machines because none of them have the same kind of network that the blue genes have. Okay, so now I want to say a little bit about some routines that were added in MPI 3. I'll say up front right now is that as far as I'm aware, these have been implemented. They're available in all the MPI 3 implementations. I'm not yet aware of any implementation that has really taken advantage of what these routines offer in terms of the potential for improving the performance of, for example, a halo exchange. One of the reasons we want to talk about them is that it's a good way often to think about what's going on with your distributed data structure update. And so even if the particular implementations in MPI, in the MPI implementation you're working with, don't give you a benefit, it's a good way to think about it. Plus, in the future, one might see implementations of these that really do take advantage of the semantics and provide improved performance. And lest you think that that's maybe not going to happen. Many years ago, on the machine from Cray called the T3D, there's essentially versions of these were used to provide the fastest halo exchange on that system by doing it collectively. These are collective operations, and essentially scheduling the communications in such a way to perform them most efficiently. Okay. So one of the things that was noted as we were thinking about this is we did all this stuff to define topologies. You've got the Cartesian topologies, you've got the graph topologies. There's no communication with those. It's just a matter of defining what processes you think are connected nearby. You can ask for a communicator to be reordered in some sense for whatever that means. In the case of Cartesian, you can ask for the neighbors. That's about it. What the neighborhood collectives give you is a way to do communication based on the topologies. So you can build a sort of collective communication with communication to the neighbors in your graph. And so there's a Cartesian communication collectives that essentially will communicate as with a cart shift with a displacement 1. These are all collective. They are collective routines, so all the processes have to call them. The benefit that this gives for the implementation is that it knows all that's going on in terms of the communication. It means that it can do things to, for example, schedule the communications to avoid contention in the network. If you had, for example, a lightweight barrier, it could use a lightweight barrier to guarantee non-interference of the messages and so forth. In terms of how these are used, buffers are laid out in neighbor sequence, so just sort of defined in a natural way for the Cartesian topologies. Sort of looks like this, so it's each process is sending in each of the coordinate directions, and have data that they're sending and data receive buffer. You can also do this for arbitrary connections by using the graph topologies, and this would really be, of course, using the distributed graph topology. That routine looks like this. So it's a neighbor all gather. You give it the data that's being sent and the sizes, then the receive buffer and those sizes, and a communicator which has to have a topology on it. And there's a couple of versions of these. There's a V version, so just like all gather V, there's a neighbor all gather V. There's an all to all. All to all is, in fact, the one that's appropriate for, say, a halo exchange, because on every edge, there's both a message going out and a message coming in. This is, in fact, the counterpart to the routine that was used on the Cray many, many years ago, which used a all-to-all V, where V allows you to say how many of each, and it just used a lot of zeros, basically do an all-to-all with my 5 neighbors and 0 to everybody else. And that actually turned out to be faster because it could take advantage of the fact that it knew all the processes that were communicating. There are also non-blocking versions of this, and so again, that can be a good way to think about operations that you're performing on a distributed data structure. You should, if you're performing an operation on a data structure as a whole, you should think of it as being performed on a whole, not as being made up of all the little pieces. And so a iNeighbor all-to-all is a way to express in a single operation that I'm going to be exchanging with my neighbors a bunch of data, and they're all going to be participating at the same time. Okay. So it gives you a way to take advantage of the topology information that you may have provided for a communicator based on the sort of logical interconnections in your application, gives the MPI implementation the opportunity to implement it efficiently. And again, whether it does that or not, over time it should improve. In any event, it's a good way to think about how you structure the communication. One way to make an MPI code completely impenetrable is to break it down into all those little pieces and then think about the communication for each piece separately. And it's much more effective to think about the global piece, this big data structure that I have divided up into pieces, and I've got operations that are performed on the global data structure, and they're done collectively, but they may be done in a non-blocking collective way, which allows me to defer the synchronization until I need to complete those operations. It allows me to provide the opportunity to overlap communication and computation. Yeah, so in summary, you've got all gather, which allows everybody to contribute some data that's then gathered to all the neighbors. You've got all to all, which gives you the what's often called, all to all is often called personalized. So the all to all here is personalized to each neighbor, not to all processes, just all neighbors in the graph. And again, we're hoping to see that the implementations start taking advantage of this. Any questions? Yeah.
So has any of this made its way into library like Prometheus, which does the decomposition?
I don't think so. Not yet. So the neighborhood collectives and the neighborhood collectives are new in MPI 3. Right? So for example, on the blue genes, you have MPI 2.2. And so you don't even have MPI 3 yet. And in order to really make use of them, you have to you do have to be careful in how you define your graph. So for example, if I have a Cartesian graph and a 9-point stencil, I have to use disgraph create. I can't use cart create, because cart just gives you connections in the coordinate directions. Right, so I believe there will be benefits for that, because again, once you know the complete communication pattern, and if you have a deep understanding of the underlying hardware, and there's sort of the question about making the code portable, so you don't want to have a deep knowledge of the hardware. You want somebody else to have a deep knowledge of the hardware. That, by having these routines, we provided a place for that to happen, right? And it needs to be done through the collective routines, because if you do it on a local basis, there are just lots of optimizations you can't apply because you don't have enough information, right? And we saw some of those this morning. So that the first example that I gave, right? If I know that everybody's doing an exchange, then I can arrange the exchange in such a way as to reduce the amount of contention. Right? I can do things. So, for example, if I had a really lightweight barrier, I could do that. If I didn't have a really lightweight barrier, but had ways to synchronize my neighbors, I might be able to do that. If I'm on a hardware network that has some hotspots, then I can order my communications to spread out the communications through the hotspots as much as possible, and so forth. Those are all things you don't want to put in your code, but they have to be somewhere, right? So what I'm hoping is that first we'll see some people, well, there has been some development of research libraries to illustrate some of these points, but those aren't really at the point that I would recommend them to be used in an application. The next level is to get those to the point where they're used as application libraries, and then from there get them into the implementations, mostly by shaming the vendors. Right? So that's often the way that it works. And so that's sort of the next step, is to get to the point where we're shaming the vendors. Okay. Yes?
With like in MPI point-to-point communications, if you're using, for example, the 3D data decomposition in stencils. So with MPI type subarrays, you can directly send it to the required location with the data. With neighborhood collectives, can you directly send it to the location where it is needed?
Yes, with the neighbor collectives, by specifying the neighbors with this graph create properly, then do a neighbor collective, it would send it to the right place. Right? Right now, I would expect that to perform essentially as well as doing I sends, I receives, wait alls, but in the future, it might do better.